Hello students, welcome back. Let's resume our discussion in section 2. This time we're going to focus upon Fermat's theorem. Here's Fermat's theorem in its original form. I mean, not the original form historically, but the original form translated in today's mathematical language. Okay, here we go. Let P be a prime number. Then the residue class Cp is a field of order P. Remember that? We proved it in 2.2 here. A residue class ring Zm is a field if and only if M is prime. Remember that? So that's the first claim. Zp is a field of order P, so far so good. And the set of all non-zero elements, Zp star, is a multiplicative group of order P minus 1. How about that? Let's see, there's no question that the order is P minus 1 because we're talking about non-zero elements. So starting from Zp, which has P elements from 0 to P minus 1, take away 0, then we have only P minus 1 elements, 1 to P minus 1. So the order is P minus 1, no question about that. Now the question is, does this form a group? Another multiplication. Well, do you recall this? Have you done that before? I hope you did because I left it as a homework in section 1, this one right here. Remember this? Let R be a ring with unity. Then the set of all units form a multiplicative group. We denote it R star or Rx. In particular, the set of all non-zero elements, Fx, of a field form a multiplicative group. So the second claim here, this one here, is actually this one here, the second claim of 1.7, except that I inserted the order. And the second claim here is, as a matter of fact, an immediate consequence of the first claim here. Why? We're talking about a field here. For fields, every non-zero element is a unit. Every non-zero element has a multiplicative inverse. So in general, for rings with unity, not every non-zero element has a multiplicative inverse, but those they do is called a unit. The units, and take all the units, then that forms a multiplicative group. If you prove that, then the second statement follows immediately too. So how do you prove that? Well, that's left as an exercise for you. Let me give you a hint, a brief sketch. The multiplication is of course associative. It's one of the standard properties of the ring, and it has the identity under this multiplication, which is called unity for the ring. And then all elements here are units, so they all have multiplicative inverses. So we have all those three properties of groups under multiplication. So the final question here is whether the multiplication is well defined. In other words, is this Rx or R star closed under multiplication? That's what you have to prove. Of course, I'm not going to do that because that's a homework problem for you. It's not going to be too hard, but it's going to be a good exercise for you to write those down. So assuming you did all that, we have everything here up to the first line. So Zp is a field of order P. Yes, we did it. And Zp star is a multiplicative group of order P minus 1. We did that too. And then finally, the punchline. The real deal. For any non-zero integer a to the p minus 1 power is congruent to 1 modulo p. That's Fermat's theorem. That's the essence of Fermat's theorem. Now here, if you multiply a to both left-hand side and right-hand side, we get the second form. A to the p power is congruent to a modulo p. And this time, it works for 0 as well, because 0 to the p power is 0. So this one down here is a little bit more general because it includes 0 as well. But this one up here is going to be more useful. So how do you prove that? Well, the key idea is this. This CP star is a multiplicative group of order p minus 1. So every element here, let's say A, or this is a residue class, so A bar, has order that divides p minus 1. And what's the order of the element? Do you remember that? We discussed it way back in lesson 4 when we started discussing the cyclic subgroups. I think we started cyclic subgroups in lesson 3, excuse me. Anyway, it's ancient story. So, the cyclic subgroup generated by this A has a certain order, and that order must divide p minus 1, the order of this large group. So a to the p minus 1 power is going to be 1. That's the main idea. So we already proved the first 2 claims, and we're going to prove the third one here. And we start with any non-zero integer, and then form a bar. You see, the residue class. And then let's consider the cyclic subgroup generated by this A bar. Then, of course, that's going to be a subgroup of ZP star. Now, this group has order p minus 1. So this subgroup must have the order that divides p minus 1. Remember that. So the order of A divides the order of the original group, ZP star, which is p minus 1. And I can rewrite it like this, but oh boy, it's really hard to read. Maybe you can read it better if I increase the font. Yeah, the order of A divides the order of ZP star. In other words, this is p minus 1, so this order times some integer k is p minus 1, so you can write like this. P minus 1 over this order is some integer k. Too big, it's hard to read. Consequently, we get this conclusion. A bar to the p minus 1 power can be rewritten as A bar to the order of A to the k power, because multiply these two, k times the order, then you're going to get p minus 1. And then what is this inside? That's going to be 1. You see, A, and this is order of A. So in the end, what did you get? A bar to the p minus 1 power is 1 bar in ZP star. And rewriting this final statement here in terms of mod p equivalence, we get the conclusion. A to the p minus 1 power is congruent to 1 modulo p. And then this one follows as well. Multiply A to both left hand side and right hand side. So that's the proof of Fermat's theorem. And before talking about any of its applications, let's consider its extension a little bit while our memory is still fresh. So instead of starting from any prime number, let's begin with an arbitrary positive integer. By the way, this extension of Fermat's theorem is done by Euler, so I named it Fermat-Euler theorem. Now, the M in this case is a commutative ring with unity of order M. Doesn't have to be a field, it doesn't have to be an integral domain. But we can consider ZMX nonetheless, the set of all units. And ZM is just a commutative ring with unity, not a field, not an integral domain in general. So the order of ZM star is not M minus 1 in general. You actually have to count appropriate element here. And what are the appropriate elements? The units. Remember that? We proved it in 2.3. A bar is a unit if and only if the greatest common divisor of A and M is 1, or A and M are relatively prime. Now, how about those A bar? Well, we have to consider M of them, right? From 0 to M minus 1. So we can count like this. The number of all relatively prime numbers between 0 and m. I mean, the number of all integers between 0 and m that are relatively prime to m. And this one here, whether I select m greater than or equal or strictly greater, that'll make no difference, because 0 and m, that GCD will never be 1, and same goes here. Even if I change this into greater than or equal, it doesn't change because GCD of m and m is not going to be 1. So either way it works. As a matter of fact, I used strict inequality, but whether you use strict inequality or semi-inequality, it doesn't matter as a matter of fact. So that number is phi of m. So number of all positive integers between 0 and m that are relatively prime to m. And this quantity is called Euler phi function or Euler quotient function. Quotient, I'm not exactly sure what this means. I looked it up in dictionary one day, but I forgot now. Anyway, that's what number theory people call. And this is very, very important in number theory as well. And Euler quotient function here, that value for prime number is p minus 1. Because p is prime, then all the numbers between 0 and p, 1 to p minus 1, they're all relatively prime to p. So phi of p is p minus 1, so we can consider this generalized into that. A2 phi of m is equal to 1. So select any element a, any integer a, that is relatively prime to m. A to the phi of m power is 1 modulo m. The idea is similar. This multiplicative group, Zm star, has order phi of m. The number of integers that are relatively prime to m between 0 and m, and those are the units, as we proved in 2.3. And then a to the order of this large group, original group, has to be equal to 1 by the same logic. So select any integer that is relatively prime to m, then form a bar, then that a bar will belong to this Zm star, the set of all units, which is a multiplicative group. And then you can form a cyclic subgroup, which is a subgroup of Cm star, and this Cm star has order phi of m. So this order of this A divides this order of Cm star, which is phi of m. In other words, this phi of m is order of A times a certain integer k. So A to the phi of m can be written as A bar to the order to the k power, and A bar to the order, well, that's going to be 1. So we end up with 1 bar. And rewriting this in terms of mod operation, we get this conclusion. If A and m are relatively prime, then A to the phi of m power is 1 modulo m. That's a generalization of Euler's theorem because it works for all n, all positive integer n, not just for prime. Okay, we went through Fermat's theorem and its extension by Euler, and we have some example problems associated to those, but looks like we won't have time to do any of those examples here. So let's stop here with just proofs, and then we're going to do the applications in a separate video. See you soon.